right? So for optimization, these are also word problems, but they're easier than the related rates because you only deal with one equation and you get it in terms of one variable. So you know with the related rates, there were lots of variables and everything was moving. The optimization is a little bit simpler than that. So the first thing that you're going to do is you're going to get an equation for what is being optimized. And whatever's being optimized is the thing that it says to maximize or minimize. That's optimization, is a maximum or a minimum. So if they say minimize cost, then you need an equation for cost. If they say maximize volume, then you need an equation for volume. So it's whatever you're being told to minimize or maximize. That's an optimal value is a maximum or minimum. You're going to get an equation for whatever's being optimized in terms of one variable. So if it's not in terms of one variable, and what that means is like if you have y equals, then you can only have x's on the other side. Like you can only have one other variable. And that's what makes this simpler than related rates, is that you get it in terms of one variable. So you may have to do like a substitution in order to get that to happen. Oftentimes you do. So it's basically just a whole big bunch of algebra. So if you're comfortable with algebra, you're going to be totally fine. And then what you're going to do is derivative equals 0. Derivative equals 0 gives you your critical points, and those give you your maximums and minimums. So that's, you're trying to optimize, so you want maximums and minimums, it's derivative equals 0. So not last class, but the class before when we did the first derivative test, it's literally that, except a word problem. That's the only difference, is it's going to be like a story, right? So let's try a few of these. So we'll give you a chance to write this down. It says two numbers have a sum of 20. The question is, what is their maximum product? Okay, Joseph wrote the answer. Can I work it out though so that you guys can learn how to do the problems if they're slightly more complicated than this one? All right, so it says the maximum product. So that means that you need an equation for the product. So product means that you're multiplying the two numbers together. So I'm going to use P for product. It would be P equals. And then you need variables for the two numbers, which I would just call them X and Y. So it would be X times Y. So the product is going to be X times Y. Now the problem is that's two different variables. So you need to substitute one of them out, and you do that by using the other piece of information. They have a sum of 20. So that means if you add them together, you're going to get 20. And so what I'm going to do is get one of the variables by itself and then substitute. And it really doesn't matter which one you get by itself. So I'm just going to subtract over the x. This would be y equals 20 minus x. And so I'm going to substitute that in for y over here. And so we'll have product equals x times, and then in place of y, we're going to put this 20 minus x. So again, we haven't done any calculus yet. We did algebra. We subtracted an x, we substituted. Now I'm going to distribute this x through there. And so now we have an equation for what we're trying to optimize. That's the product in terms of one variable. I only have x's over here. And so then it's derivative equals 0. So we're going to do p prime equals, and this derivative would be 20 minus 2x. We're going to set that equal to 0. And then you would subtract over the 20. And so x is 10. Divide by -2, you get x is 10. So these problems are very heavy on the algebra. The only step of calculus I did was taking the derivative. Literally the rest of this is a bunch of algebra, so you just have to, fight your way through it. All right, now we're not quite done. It says x is 10. I need to know what y is. So if you plug 10 back in for x, 20 minus 10 is 10. And if both numbers are 10, then the product is 100, 10 times 10. So what you get is that the optimal way to do that is for them to be the same value. And you'll see that that happens a lot. Okay, so now you can obviously, as Joseph showed us, get through that without actually doing any work, but it's still important to know the process for how to do this because they're not all going to be that simple. But let me just throw another one out there. Try to just jump straight to the answer. If two numbers have a sum of 10, so say I made it 10 instead of 20, if two numbers have a sum of 10, what would be their maximum product? Yeah, good. And it would be 25 because if their sum is 10, then both the numbers would be 5. You'd have 5 times 5 is 25. All right, so let's try another one. All right, so we're gonna fence in a rectangular pasture for our sheep or our cows or whatever. But it's against the side of a barn. There's a couple reasons you'd want to do that. The barn will act as one side of the fenced-in area. So you don't have to fence that side. So just as a heads up, this one is not going to end up being a perfect square because I threw that extra piece of information. I threw the barn in there. So it's not going to end up being a perfect square for this one. It's going to be off a little bit. All right, so we're fencing in against the side of a barn. You can use 48 feet of fence. We want to maximize the area for our animals. Okay, so I'm going to draw a picture. Don't make fun of my drawing. Here's a barn. This is how I would draw a barn. And so we're going to fence in. Here, I'll use colors here. They don't show up very well on the projector, but we're going to fence in against the barn. And we're doing that so that we only have to use 3 sides of fencing. And so I'm going to use X and Y for the variables there. Now, just to let you know, if say the barn wasn't there, say I didn't put a barn in this problem, then it would be a perfect square. And each side would just be, 24 feet. But because of the barn, that's going to change that. All right, now we want to optimize the area. So I need to write an equation for area. So for a rectangle, the way you get the area of a rectangle is x times y. It's going to be base times height, or length times width. So it's going to be x times y for the area. Oh wait, I'm getting a lot of questions there. You wouldn't assume the barn is infinitely long. We only have 48 feet of fence, remember. This amount of fence replaced by like that's what's going to happen. We want to maximize the area. Just hold on. I think you guys are again trying to jump straight to the answer. Let me actually work it out and show you the calculus, because I think once you see it worked out, you will understand it. So can you just give me a minute? Yeah, you can presume that the barn is long enough as you need it to be. Not infinitely long, I was supposed, but it's big enough for the purposes of this problem. All right, so the problem with this equation is, okay, that's what you meant. Sorry, when I see infinitely long, I think of a barn that wraps the whole way around the earth, and that's not the case. But you can't assume it's big enough for the purposes of what you're trying to do. All right, so the issue is we have x times y. That's 2 separate variables, so we need to substitute one of them out. And so we're going to go back to the information in the problem. We have 48 feet of fence. So if I add up these three sides, it's going to equal 48. So if I add up these three sides, it would be 2y plus x equals 48. All right, and so in the previous problem, it didn't really matter whether we solved for x or y. For this one, I think it's definitely easier to solve for x since it doesn't have a coefficient. So I'm going to subtract over the 2y. Again, guys, remember it's just a bunch of algebra. Just subtract it over the 2y. And then this is going to get substituted in for x. So we'll have area equals 48 minus 2y times y. And then I'm going to distribute the y into there. So 48y minus 2y squared. And we now have our area in terms of one variable. And so here is the one step of calculus, is we're going to do derivative equals 0. I'll be honest with you, this is the most commonly missed step in the whole thing because people get, so focused on all this algebra and they'll forget to take a derivative entirely. And it's like the most important step because it's the only calculus in the problem. So don't forget to do a derivative. All right, so this derivative would be 48 minus 4y. We're going to set that equal to 0. The reason why you take a derivative is you're trying to optimize, and that means maximums and minimums. Maximums and minimums come from critical points. So derivative equals 0 gives you the critical points, and that's where you get maximums and minimums. All right, so we're going to set this equal to 0. So I'm going to subtract over the 48. And so y is 12 feet. And so that's y, but we still need x. So I'm going to plug 12 back in for y right here. So I'm going to plug 12 back in for y. 12 times 2 would be 24. And 48 minus 24 would be 24. So 24 feet. So let me write that in the picture here. Y would be 12. And x would be 24. And so to get the total area, you're going to multiply those together. I don't know what that is off the top of my head, so I'm going to type that in here. 12 times 24, 288. And let's talk about units just real quick here. We found an area. So the units aren't going to be feet. What are the units going to be for this one? Yes, it will either be feet squared or feet cubed. It'll be one or the other. One of those is for a, yeah, good. Cubed is for volume. So squared is for area. That's why I bring it up, because it's a simple thing to mix up. So that's why I like to bring it up. All right, we're just going to do a couple more. All right, number 3. All right, while you're writing that down, I'm going to real quick make one of these boxes so that you can see what I'm talking about. So write down the problem. Also, you will need a calculator for this one. So if you have your calculator handy, go ahead and get that because you're going to need it for this. And the box that I make here is not going to be like perfect. It's going to be good enough here. All right, and this, by the way, is a really famous calculus problem. Every student in the entire United States around the world that is taking calculus is going to do this problem. Everybody everywhere in the world taking calculus, they're all going to do this, all right, when they do optimization. So when you have an 8.5 by 11 sheet of paper, so that's just this regular sheet of paper. Let me zoom out. What you do is you cut, oh, that's the farthest I can zoom out. What you do is you cut the corners off of the piece of paper, and then you fold up the edges to create a three-dimensional box. Can you guys see that well enough to like understand what I'm talking about here? Like, is this making sense? Mine has holes in it. It's gonna like leak because of the paper having, anyway. Okay, cool, good. So that's what we're creating. So you have this piece of paper and you cut the corners out and then fold it up to make a three-dimensional box. And so what we want to do is maximize the volume of the box. So that's what we're trying to optimize, is the volume. So I need an equation for volume. So the volume of a box is going to be length times width times height. And so let me draw a picture of the piece of paper off to the side here. Here's our 8.5 by 11 piece of paper. And what I'm doing is cutting a corner out of each side. So if we're going to do the length of the box would be from here to here. This is the length. So it was 11, but I cut a corner out of each side. And so I'm going to call that distance x. That's what we don't know, is how much do we want to cut out. So the length of the box would be 11 minus 2x. You've subtracted 2x on each side. One for each side of the piece of paper. And then the exact same thing is going to happen for the width. It was 8.5, but we cut a square out of each side. And again, I don't know what that amount is. That's what we're trying to figure out. But I cut that off of each side. So this would be 8.5 minus 2x. So that's length times width. Then I need to multiply that by the height. Well, if you fold it up, so here's again the one that I made. If this distance is x, when I fold that up, do you see how x becomes the height? The height of the box is that x distance. So the height is x. So this is length times width times height. Now, the good thing is there's only x's, so we don't need like a secondary equation to try to substitute. The bad news is we do have to multiply all this together, but it's just going to be a lot of distributing. We can do it. You're allowed a calculator for this one, so it's going to be okay. All right, so first I'm going to multiply these two together. So 11 times 8.5. 11 times 8.5, I'm just typing that in. Ooh, whoops. Messing up my button pushing there. 93.5. All right, and then the outsides, 11 times negative 2. So that would be negative 22x. And then the insides, negative 2 times 8.5. That would be negative 17x. And so together that is negative 39x. And then negative 2x times negative 2x, positive 4x squared. And then we've still got this x hanging on at the end. It's just a bunch of distributing. You're just multiplying everything together. If algebra was your subject, if you're like, I was good at algebra 1, algebra 2, this is like your thing, because it's basically just a bunch of algebra. All right, and then we're going to distribute this x through here. So 93.5x minus 39x squared plus 4x cubed. And like I said, the most common mistake with these questions is people will forget to take a derivative. They'll just go and set this equal to 0. Just please remember to actually do the derivative. That's what gives you the critical points. All right, so this derivative would be 93.5 minus, gosh, what is that going to be? 78x plus 12x squared. We're going to set that equal to 0. Now here's where the calculator comes in, because this does not factor. If you could factor that apart and set the factors equal to 0, then you'd be okay, but you cannot factor this. So if you want to follow along in your calculator with me, go ahead and go to y equals, and I'm just going to type in that equation. And I'm going to make my window -10 to 10 for all these. Or you could hit zoom standard, zoom 6. I don't know what it needs to look like, so I'm just going to make it be standard. Oh yeah, I would not do, I've never seen a problem where you, well, I don't want to say never. In math, there's always like some exception. I cannot immediately think of a problem where you have ever had to do the quadratic formula in AP calculus. We also don't do imaginary numbers. That's like a whole thing that you learn that we don't even do at all. Not that they aren't important, but we don't touch imaginary numbers in calculus. All right, so here's the parabola. Yeah, I don't hate them. I think I like that we don't deal with them here. I think there's enough else that's going on. All right, so you're going to notice there are 2 critical points. So which one do we want? Well, we want to maximize the volume. So that would be a change in the derivative from positive to negative. So the one we want is this first one. Here's the good news. If you forget and you pick the second one, you're going to end up with a negative volume at the end. And then you'll go, oh, I must need to get the other one. So you like almost can't mess it up, because if you pick the wrong one, it's not going to make any sense. Right, so we need to calculate this 0. So I'm going to go to second trace. And we want to choose a 0, which is number 2. And it looks like it's in between 1 and 2. So for my left bound, I'm going to do 1, enter. And for my right bound, I'm going to do 2, enter. And for my guess, I'm going to put 1.5, enter. And it will literally just come up. Like that's the x value. X equals 1.585 inches. So 1.585 inches. Now, if you want the actual volume, you have to take that 1.585 and plug it back into this original equation. Here's the really cool thing that your calculator will do for you. As of this moment right now, and listen carefully, because this is nice that this will do this, all right? As of right now, it has x stored as this number that we want to plug back into this equation. So if you quit out of here and go to the home screen, if you just type this original equation literally exactly like it looks with the x's and everything, what your calculator will do is plug in this 1.585 decimal. It'll plug it in for the x for you. Like it has x stored as this. If you type that original equation just exactly like it looks and hit enter, boom, there's the answer. So 66.148. And what would be the units for this one? It will be cubed. That is correct. For volume, it will need to be cubed. But yeah, good, inches cubed, because it was just a little piece of paper that we were using. So that's kind of interesting. If you had, you know, an 8.5 by 11 piece of paper, if you wanted the largest volume box, you would cut roughly 1.5 inches out of each side. Like you would cut out 1.5, and this would be the biggest volume that you could get. That feels like a lot of volume just from a little piece of paper. So I think that's cool. This is cool. It is. All right. I just want to do one more. This will be the last one here. All right, so this is going to be a rectangular tank with an open top. I have to tell you a funny story about doing this problem. I had a class one year let me get the whole way through this question, and then they asked about the tank. They thought I meant like a military tank. Like, hey, we're coming to get you. I mean like a fish tank, like a rectangular fish tank that would hold water, and the top is open. Yeah, that was my reaction too. The top is open, like there's not a lid. That's what that means, that there's not a lid. So there's a bottom and 4 sides. There's not a lid, but it's like a tank that you would put fish in, okay? Not like we're in the army, okay? But ever since that day, I have specified, I didn't think that needed clarification, but you know, I'm always surprised. So, all right, so the width is 4 meters. This is really big. This is like a, you know, an aquarium fish tank. We're in meters here in fish driving a tank. I know, like, it never occurred to me that and like the whole class thought that. I was like, I don't know what happened here, but anyway, like a really big fish tank, right? So the width is 4 meters. The volume is 36 cubic meters. And then I'm going to tell you the prices of the materials. So the bottom of the tank costs $10 per square meter. And the reason that's squared is just the bottom would just be an area. That's just two-dimensional. And the sides cost $5 per square meter. So the bottom of it is more expensive. I guess like it has to be sturdier than the sides. So all right, and we want to minimize the cost. So we want to spend the least amount possible. So I will draw a picture of this. And I even drew a picture of it then too, so I don't understand at all what happened. But anyway, here's the rectangular tank. It's like a fish tank. This is the extent of my artistic abilities here. All right, there we go. All right, so the width of it is 4 meters. So here I will color code. So this is 4 meters. And we weren't told specifically the length or the height. So I'm going to make the length be x and the height be y. We need variables for those. They told us the width, but we don't know the length or the height. So I'm going to call those x and y. Now we do know the volume is 36 meters cubed. So if we were going to do the volume of this box, that's length times width times height. That would be 4 times x times y. That's going to be 36 for the volume. Now I wrote that out because it's true and it's written right here, and we are going to need that, but we need to write an equation for cost. Cost is what we're trying to maximize, or sorry, minimize. We want to spend the least. We don't want to spend the most. We want to minimize cost. We want to optimize cost. So I'm going to need an equation for cost. We're going to do cost equals. All right, so let's do the bottom of the tank first. So this area right here. So that area would be 4 times x, and it costs $10 per square meter. So it's going to be an area of 4 times x, that part I shaded in there, and it costs $10 per square meter. So we're timesing that by 10. All right, and then next we're going to add up the sides. Now I can't do all 4 sides at once because they're different areas. So here, I'm going to totally ruin my picture here, but let's do these sides first. So they cost $5 per square meter, and the area for that would be 4 times y. So this dimension is 4, and then the height is y. So it's $5 per square meter, and the area is 4y, and we have 2 of them. So I'm multiplying it by 2 because there's this side and there's this side. So there are 2 of them. All right, and then lastly, I'm going to do the other 2 sides. So that would be this one. Gosh, I've totally ruined this picture at this point. This side and then the one on the other side. So again, it's $5 per square meter. That area would be x times y. And there are 2 of them. There's this side and there's that side. All right, so let's clean this up a bit because this is like a big old mess here. This would be 40x plus 5 times 2 is 10 times 4 would be 40y plus 10xy. So here's the issue. We have x's and we have y's. So I need to substitute one of them out. And so over here, I'm going to solve for y. So I'm going to divide over this 4x to get y by itself. And then we can simplify that. 36 divided by 4 is 9. So it'll be 9 over x. So that is going to get plugged in for y in this equation. Again, stick with me. It's just a bunch of algebra. We're substituting that in. All right, so this is going to be 40x plus 40 times 9 over x. I'm plugging 9 over x in for y. Plus, and then this would be 10x times 9 over x. So now we want to do derivative equals 0. Let me again just like simplify this down a little bit. And you're like, this is so much writing, Ms. Cole. You're going to be okay. It's going to be all right. Pep talk. You're all going to be fine. Let me just simplify this a little bit before we do the derivative. This would be 40x plus 40 times 9 would be 360. And this is an x to the negative 1. It's in the denominator. That means a negative exponent. So x to the negative 1. And then over here, the x's are going to cancel, so we'll just have plus 90. And so now it is derivative equals 0. So this derivative, this would be 40. Here we're going to do a power rule. So the negative comes down. It's going to be a negative 360, x to the negative 2. 90 is a constant, so it's gone. Set it equal to 0. That'll give you your critical points. And then we're just going to solve this for x. So I'm going to subtract over the 40. That'll make this a negative 40. I'm going to fix this negative exponent. This would be negative 360 over x squared. Again, all that good algebra, all of your exponent rules there. And so then I'm going to multiply over the x squared. And then we'll divide by the negative 40. So negatives are going to cancel. So it'll be 9 equals x squared. And so x is 3 meters. All right, so if x is 3 meters, what is y? If x is 3, plug that back in for me. If x is 3, what is y? Good, 3. I know you're shocked that they came out to the same thing. Typically, when you're optimizing, the best thing to do is have them all be the same. So, you know, these would both be 3. So my picture is not correct here, right? So those are both 3. And then we want the cost. We want to know how much dollars, cash money, this is going to cost. So I'm going to go back to this original equation here. Or I guess we can use the more simplified one. Let's use this one because it's a little bit more simplified. I'm going to plug in 3 for x and y. So let's see. 40 times 3, that would be 120. Plus 40 times 3 would be another 120. Plus 10 times 3 times 3, that would be 90. And so I just added all that up. $330 is how much this tank is going to cost.